Hello everyone, I'm Shravan Kodavanti and today I'm honored to present our work on unlocking edge deployment for multi-LoRa foundation LLMs. This project is a collaborative effort between Samsung Research India and Samsung Research Korea. Our research focuses on bridging the gap between flexible adaptations of server-side LLMs and the rigid high-performance requirements of native mobile hardware. The challenge of edge deployable AI, that is on-device AI, isn't just about the size, but it's about the runtime flexibility. While server side we had unlimited virtual memory and compute, and on server side the models dynamically recompile on the fly, and they can also handle multiple LoRas for multiple use cases by statically compilation of those LoRas during the model inference. But that's not the case for mobile device scenario. Mobile phones operate with frozen inference graphs and stringent memory limits. So all these operations need to be logged into single frozen inference graph. So one can't maintain different types of graphs for different use cases or different LoRas. So one need to suggest a new way of maintaining multiple LoRas and multiple graphs for the model. And the recent most techniques like speculative decoding and all may not be fit into mobile phone scenarios because the draft model may occupy enough extra room on the mobile phone. To mitigate all the problems for deploying an LLM on device, the system demands optimization across memory, compute, and decoding. And here I am mentioning what optimizations that we had done for deploying an LLM on device. Coming to handling multiple LoRa's for multiple use cases, we pass LoRa as input to the model instead of attaching it to the weights of the model. And also we perform in-for quantization, thereby reducing the bit precision of the model. And for using effective use of the mobile NPUs, we do sorts of transformations such as converting a linear blocks to convolution blocks, and we also convert multi-head attention into single-head attention. And we also perform different kinds of decoding strategies such as concurrent token generation, where we generate multiple synthetic streams of an uh, output for a single input. And we also do dynamic self-speculative decoding, where there is no draft model, so there is no any extra draft overhead for the self-speculative decoding, and it is very suitable for mobile phones. To solve the LoRa flexibility issue, we reimagine how LoRas can be handled. Traditional static merging of LoRas lead to system crashes and out-of-memory errors when scaling to multiple use cases. So we propose LoRa weights as runtime inputs along with the text tokens, which I had mentioned in the previous slides. By using placeholders in a single frozen graph, we enable dynamic task switching between summarization and smart reply use cases without any latency penalty of graph recompilation. So by using this LoRa as input technique, our 1B model tests on Galaxy S24 reduces the model size from 894 MB to 686 MB while cutting the latency by nearly 30% from 75 ms to 52 ms. We also re-engineered the transformer architecture to realign with mobile hardware strengths. Firstly, we transform a dense linear layer into one cross one convolutions. Why are we doing it? This transformation allows us to export highly optimized Vinograd kernels and vision centric hardware accelerators that are already present on the Qualcomm hardware chipsets in the mobile phones. Secondly, we decomposed multi-head attention into parallel single-head paths, allowing the NPU to schedule operations across heterogeneous cores independently. And we had also done graph compilation strategy optimization, where we do constant folding, that is pre-computing static tensors and operator fusing and all, which minimizes the NPU kernel launching overhead. Coming to decoding strategy optimization, one of them was concurrent token generation, which is nothing but CTG. So, what was the main idea behind it? Generally, personalization features like smart reply often requires multiple tone options such as formal, polite, and casual. So, sequentially running these would increase the latency by 8x. So, how are we solving it? Our CTG algorithm uses a masked decoding scheme and shared KV cache to generate up to 8 stylistic variants simultaneously in one forward pass. These results in a massive 6x reduction in latency, dropping from 174 ms sequentially to just 63 ms concurrently. To further accelerate the token generation, we introduced a new novel decoding strategy called DS2D, Dynamic Self-Speculative Decoding. Unlike the standard speculative decoding methods, DS2D does not require any secondary draft model, saving the space of draft model on the mobile phones. We use prefix tuning strategy to train the LLM to predict multiple future draft tokens for each and every inference, effectively making an autoregressive model into semi-autoregressive one. And to make sure this optimization is a lossless approach, we also perform tree-based verification strategy for the generated draft models. And the number of draft tokens generated in each and every inference is 1 plus m, where m is an hyperparameter. And since the technique is called dynamic self-speculative decoding, the hyperparameter is varying for each and every use case. And coming to the diagram here, the inference step N1, inference step 1 will generate the draft tokens, and inference step 2 will verify the draft tokens generated by inference step 1 through the tree-based verification. Using this tree-based verification strategy and DS2D technique, we achieved an average of 2.3 speedup in decode time on Galaxy S25 Ultra mobile phone. This pushes the performance across all commercial use cases. Our empirical results demonstrate the framework scalability of DS2D. Across multiple use cases, the decode time has been reduced from around 50 millisecond to 20 to 22 millisecond. And coming to tokens per second improvement, it was increased from around 18 to 19 tokens per second to 35 to 45 tokens per second. This was a substantial increment of around 2.3 speed up. And across 9 different languages, including Korean, English, German, Japanese, and across 8 different tasks. Finally, coming to quantization schemes, we used INT4 bit precision for weight quantization and INT8 bit precision for activation quantization, and this reduced the ROM by 3x. The floating point model is around 1800 MB, which is like 1.8 GB, and the quantized INT4 LLM is around 600 MB. So we got a ROM reduction by 3x. And coming to accuracy perspective of the quantized model and the floating point model, we use LLM as judge as our accuracy metric, and we calculate the relative accuracy between the floating point model and the quantized model. Our empirical results suggest that across 9 different languages and different tasks, the relative accuracy of the quantized model compared to floating point model is around from 96% to 109% for the 3B model, and it is also in the same range for the 1B model, which proves the quantization does not affect the accuracy perspective as well. This framework is not just theoretical. It has been successfully commercialized into Samsung Galaxy S24 and S25 Galaxy AI ecosystem. It powers high-impact features like writing assist, summarization, and health energy scores entirely on-device, preserving user privacy by never hitting the cloud. By bridging the gap between server-scale flexibility and immutable edge hardware, we have high-performance on-device generative AI. Thank you. Please scan the QR code to read the full paper.